In section 7.2, we take what we learned from 7.1 with graphing systems of inequalities and put them to use in a business application sense. In the business world, we call this linear programming, which kind of threw me because when I think of programming, I think of computer programming in specifics. But linear programming is a graphical method of optimizing values. So the goal of optimization is always going to be to find the maximum or minimum value of certain functions, such as profit, cost, or revenue. Now, some of these we want to maximize, some of them we want to minimize, right? Profit. For sure we want maximum profits, so that would be one we would want to maximize. Cost function, though, we are typically going to want to minimize our costs. And then revenue, that's bringing money in, so we're probably going to want to maximize revenue. So whether we're looking for a maximum or a minimum function value depends on which function we're working with. Now, when we're talking about graphically doing this linear programming stuff, we have some new terminology. The objective function is our objective. Totally makes sense, you know that word. The function, cost, profit, revenue, etc., for which a maximum or minimum value must be found. We want to optimize this function. This function, my objective function, is usually designated z, and then whatever the function is. So whenever you see z equals, especially for this book, you know that that's your objective function. The constraints are the constraints or the limits where we need to operate. Functions that represent various limitations are constraints. So transportation costs, environmental protection laws, availability of parts, interest rates, capacity issues. These are all business constraints that limit your production, that limit your distribution, that may be monetary constraints, things that limit these maximum and minimum values. Now notice we're only going to be focusing on one objective at a time, but you can have multiple constraints. These constraints are our boundary lines. So this is where we look at graphing those inequalities. The constraints are our boundary lines. Okay, so consider this particular objective function. My key that it's the objective function, it is z equals 2x plus 5y. Suppose that z represents cost. Would you want to minimize or maximize it over a feasible region? What do you think? Well, usually we are going to try to minimize cost, right? We want to keep our costs low. What if z represents profit? What are we going to do? Well, we want to make more money, right? So we want to maximize our profits. All right. We always have to work within constraints. Here you can see that we've got 1, 2, 3, 4, 5 constraints. These are our axes, but they are also acting as constraints. I know they're acting as constraints because I can see where my feasible region is shaded. So I have 5 constraints here. My feasible region is what we call bounded, which means that it's enclosed on all sides. For example, if I took away this green line, I would be shading all the way. Well, no, I would still be bounded by these. How about this? How about I took away the red line? If I take away this red line, this shaded area is going to keep going forever this direction. That would be unbounded. But this one is bounded. I have 1, 2, 3, 4, 5 constraints. This constraint 3x plus 2y less than or equal to 6 is this red line. The constraint negative 2x plus 4y less than or equal to 8 is that blue line. The constraint x plus y greater than or equal to 1 is the green line. And then I've got my axes as my 4th and 5th constraints. You can see that these are bounded. I have 1, 2, 3, 4, 5 corner points. Now those corner points are where I'm going to find maximum and minimum values. So if a maximum and or minimum value exists, it will always occur at a corner point. So when you are checking to find a maximum or checking to find a minimum, you only have to check those corner points. Now this is, for this problem, this is my objective function, and we don't know if this objective function is cost, profit, revenue, so we don't know if we would want to maximize or minimize it. But the way I would check to see where the maximum and minimum values are would be to find those coordinates and plug them into my function and see what value I get for z. Now, don't make the mistake of just assuming, oh look, this one's high, this is maximum. Oh look, this one's low, this is minimum. Some of that is logical, but you cannot be assured on every problem that you can look and predict. So I'm going to ask you to find the function values at each corner point a lot. Now some of these corner points are easy. Right here, this is on my axis, so the coordinates here are going to be 0, 1, and here I've got 1, 0. This is also on an axis, so this is going to be 2, 0, this is going to be 0, 2. But how do I find, for example, the coordinates of this corner point? Well, all of these corner point coordinates are points of intersection. So when I'm intersecting on an axis, it's easy. If it's not on an axis, I have to find the solution to the system of equations, which ties us back to our last unit. You know how to solve systems. We can add, we can substitute. All right. So this section is where we really start putting together a lot of the new things that we've learned this semester. Corner point theorem. If the feasible region is bounded, then the objective function has both a maximum and a minimum value, and each one of those is going to occur at one or more corner points. If the feasible region is unbounded, it may not have a maximum or a minimum, one or the other. But where those maximum and minimum values exist, they will occur at one or more of the corner points. Okay? These two are bounded regions. This one is a bounded region. A lot of what we work with are going to be bounded regions, but just be aware that we will get to some that are unbounded. Okay, we're going to optimize our objective function. Use the feasible regions that are already shown for us to find maximum and minimum values of each given objective function. Now, it doesn't tell us what type of function, objective function we have, so we don't know whether we're going to need maximum or minimum. What I want you to do is go ahead and number your corner points. We've got 1, 2, 3, 4 corner points here. And we are going to find the value, the function value, for each of those 4 corner points. So for corner point 1, I've got coordinates 5, 10. So z is going to be 6 times 5 plus 10, which is 40. For corner point 2, my objective function z, I have 6 times 6 plus 3, which is 36 plus 3 is 39. For corner point 3, my function value z is 6 times 1 plus 1, which is 7. And then my fourth corner point over here is z equals 6 times 2 plus 7, so that's going to be 12 plus 7 is 19. Well, my function values, I see that I have a maximum function value here and a minimum function value there. So I have a maximum at this first corner point, 5, 10, and I have a minimum at this third corner point, 1, 1. Now that does, visually that was what we would have expected. but you cannot always be sure that it's going to come out the way you look at it and assume. Okay, I want you to do the same thing on this second one. I want you to identify your corner points. Let's number them together. 1, 2, 3, 4. This time we have 5 corner points. You're going to find the values, the function values, objective function values for all 5 corner points, and then identify where your maximum is and where your minimum is, which corner point. Pay attention, you've got decimals going on in here, so this function value z is going to be 0.35 times 6 plus 1.25 times 18. That should come out to be 24.6. I want you to plug those in, pause the video, plug those in, find your function values for each of these 5 corner points. I'm sure you probably were able to predict your minimum at the origin, probably your maximum up there at the 0.618. For this next one, we're going to be finding the corner points. So there we found the function value. We optimized the objective function. Now we're going to be finding the corner points. Identify the system that needs to be solved to find each corner point. Now, we have 4 different constraints. 1, 2, 3, 4 different constraints. We don't ever have to find a solution to a 4-equation system. We have to identify which 2 equations are used for that point. So, for example, point A, right here, it's on the intersection of these 2 lines. So I would have to solve x equals 3 with y minus 2x equals 2. That's the system that I would solve to find the coordinates for A. And I've got to solve these systems. I do not want to guess. I could guess wrong. I'm not assured that I'm going to have integer coordinates, and none of these are on my axes. So I've got to solve systems for each of these. Corner point B down here is on the line 3y minus 2x equals 0, as well as x equals 3. So that would be the system that I solved to find the coordinates for B. Corner point C is on the 2 lines 3y minus 2x equals 0 and y plus 8x equals 52. And finally, corner point D on those 2 lines. So that's the system that I would solve to find the coordinates for that corner point. Is this feasible region bounded or unbounded? Well, it's bounded because it is restrained on all sides. We're not actually going to work through and find these coordinates for these corner points. We're just going to make sure that we understand what we would need to do. The next one we're going to work out, we are going to work through the process. Okay, so we have our boundaries graphed. We've got 1, 2, 3, 4 boundary lines. 2 of those are our axes. These other 2 are linear, but they're not our axes. We're given our objective, and we're told we're going to minimize our objective function subject to these 4 boundary lines. Now, we need to identify our feasible region, make sure that it is, I'm expecting it to be this bounded region in the middle, but depending on which way I would need to shade this equation, if I shade it up, that's gonna change. That would make my feasible region up here instead of inside here. So I've got to make sure that I shade the right sides. For this first boundary line, x plus y less than or equal to 10, if I go to the origin as my test point, I would have 0 less than or equal to 10. That's good. I'm shading down here. For this boundary line, again, let's test the origin. 0 greater than or equal to 6, that's false. So I would shade this way. So we're looking good so far. X greater than 0. My x value greater than 0 is to the right. My y value greater than 0 is up. So yep, this is our feasible region inside here. So excellent, excellent. We have 4 corner points. Let's label these corner points A, B, C, D. Anytime you see these 2 restrictions, x and y both greater than or equal to 0, we know we're in quadrant 1. We've identified quadrant 1. We know that our feasible region is bounded now. We did not make an assumption. We checked it. We know that our feasible region is bounded. A lot of times what we're doing is going to be limited to quadrant 1 because all of our things that we are working on are going to be positive values. You know, money, products, we need to keep these things positive. Time, these are all constraints that are going to be positive. You can't have negative numbers of hours worked. Okay, let's find our coordinates for our corner points. These 4 corner points are all on axes, and so I can write my coordinates pretty easily. This one is going to be at 2, 0. This one is at 0, 2. Up here we're at 0, 10. And over here we're at 10, 0. So we've got our 4 corner points, A, B, C, and D. I have the coordinates for each of those. And I have my objective function that I want to minimize. So probably a cost function. We tend to want to minimize costs. So we want to find, because I'm telling you to find them all, not guess. We want to find all of these values. If x is 0, y is 10, my function value is 20. Where x is 10 and y is 0, my function value is 10. Where x is 2 and y is 0, my function value is 2. And where x is 0 and y is 2, my function value is 4. So my minimum is here. My function is minimized at that point 2, 0. Now this came out the way looking at it, I would have guessed. But depending on how each of these coordinates is weighted, it could go a different way. So again, don't make assumptions before you check the math. For those of you who like things written out step by step, here you go. Solving a linear programming problem graphically. Write your objective function and constraints. Graph the feasible region. Determine the coordinates of those corner points. Find the function value at the corner points. And then if it's bounded, your solution is going to be given by the corner point producing that optimum value, either the maximum or the minimum. Alright, we're going to do one more practice problem together. Got a lot of white space on this page, don't we? Okay, so I am going to start by identifying my x and y axes, and notice that I bring that in 1 so that I can mark on the outside. I can decide where my labels are going to go on my axes. So here's my x-axis, here's my y-axis. I have an objective function that I'm asked to minimize, so probably cost. And then I have 5 constraints. My first 3 constraints I'm going to have to graph. My 4th and 5th constraints mean that I am limited to quadrant 1. So that's why I went ahead and sketched in my x and y axes, because I've got x greater than or equal to 0 and y greater than or equal to 0 right there. Now I need to graph these first three constraints. So my first constraint, 2x plus y, the boundary line is going to be at equals 10. This is going to be a solid line, solid line, solid line. All of these are going to be solid lines. Usually that's the case. Doesn't hurt to check. If I find my intercepts here, if x is 0, y is 10. And if y is 0, x would be 5 because I'd have to divide. So there are my intercepts for this first line. So 0, 10, and 5, 0. You know what? Before I start graphing, I may want to think about what all of them are going to be so that I make sure I measure out how if I need to count by 1s or 2s or 5s or whatever on my axes. So my second boundary line is at 5x plus 2y equals 20. These are my boundary lines I'm working out, my constraints. My boundary lines are constraints. Okay, so this is where my next one will fall. If I do intercepts, if x is 0, y is going to be 10 because I divide by 2. If y is 0, divide by 5, and I get that x would be 4. So those are my intercepts, x and y intercepts for my second line. My third boundary line is at negative x plus 2y equals 0. If x is 0, y is 0 here, so it goes through the origin, but that doesn't give me a second point. So let's solve for y. Let's do 2y equals x and then plus 0, so I would divide both sides by 2, so I get y equals 1/2 x is my boundary line here. Looking at these point values, I can count by 1s. That's not going to be a problem. So if I count by 1s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, tiny little lines, close together lines, so I don't worry about trying to write numbers down on each of them. I just want to keep myself straight. I'm not needing to graph beyond 10, so I'm good. My first boundary line is at 0, 10 and 5, 0. Nice, straight, solid lines. So that's my first boundary line. My second boundary line goes from 0, 10 to 4, 0. 0, 10 to 4, 0. Ooh. Really close together, aren't they? Just a little bit different slope. So there's my second boundary line. That's 1, that's 2. My third boundary line goes to the origin and has a slope of 1/2. So starts at the origin, goes up 1 over 2, up 1 over 2. That's my third boundary line. Now I need to figure out where I am shading. What is the region that I need to shade in? I'm looking for a lighter colored pen. Okay, what region am I going to shade in here? Well, for my first boundary, if I check I can check the origin on the first two. If I check a test point here, I would test 0, 0. 0 less than or equal to 10 is true. So for my first boundary line, I'm going to shade down toward the origin. For my first boundary line, I'm shading down toward the origin. My second boundary line, I can also test the origin. Second boundary line, 5x plus 2y greater than or equal to 20. So 0 greater than or equal to 20, that's false. 0 is not greater than or equal to 20. So when I shade for the second line, I'm shading up the opposite direction away from the origin. So, okay, so that's good. So I'm shading between these two lines. I know that so far. The question is, what about this third line? Am I going to shade up here or down there? Well, I can't check the origin this time. I can't check the origin because it's on that line. I could check the point 3, 0. But if I check that point 3, 0 and I plug it into my inequality, I get negative 3 plus 0 greater than or equal to 0. Well, negative 3 greater than 0 is false. So this point is not included in my inequality for this third boundary line, which means I'm going to shade up. If I'm shading between these two and up above this one, that means this is my feasible region that I'm interested in. This little wedge right here. All right, now I did not draw that super well. Both of these lines should go through that same point. So this first point is at 0, 10. And I know they both go through that point because those were the intercepts, the y-intercepts for both of those lines. So 0, 10 is this first corner point. I have a corner point here and a corner point there. This corner point, I used my slope to get there. I went up 1 over 2, up 1 over 2. This corner point is at 4, 2. I can be confident of that. But this corner point appears not to be a nice integer set of values. So to find my coordinates for C, I'm going to have to solve that system of inequalities. C sits on my second and third constraints. That's my system, second and third constraints. So my second constraint is 5x plus 2y, and we're going to do equals 20. And then my third constraint, negative x plus 2y equals 0. If I multiply this equation times a negative 1, times a negative 1 there, not going to change the first one. This would become x minus 2y equals 0, and I could add that. I end up with 6x, that adds to 0 equals 20. So x would be 20 over 6. I can simplify that to 10 thirds. So that's the x coordinate. And I'm going to take that, I'm going to plug it back in. I can plug it in here into my third equation. Negative x, negative 10 thirds, plus 2y equals 0. Well, now how can I find the y value here? A couple of different paths I can take. I'm going to choose to multiply everything by this denominator to clear out fractions for the beginning. So that's going to cancel, leave me with negative 10. That gives me minus 6y equals 0, because anything times 0 is 0. So if I add that 10 to move it over, I have negative 6y equals 10. And then I divide by negative 6. Gives me y equals a negative 10 over 6 is going to simplify to be 5 thirds. So the coordinates for point C are 10 thirds and oh, that should be positive. I hope you guys were all squealing and squirming right there. That should be a plus 6y. Yeah? What am I doing to myself here? This should be end up being positive. Oh, that was not a negative 10 thirds. That's what happened. Nothing negative about that 10 thirds. So when I move it over, I have a positive 10. So when I subtract it, it becomes a negative 10. And negative divided by negative is positive. And that's how math works, guys. I knew that this could not be negative because I'm sitting here looking at point C and it's in quadrant 1. C has to have both coordinates positive. So I knew I had messed something up. And then I just went back and worked through to find my mistake. Everyone makes mistakes. The trick is learning to identify where your mistakes were made so that you can, first of all, notice you've made a mistake and then identify where they were made so that you can figure out how to correct them. Okay, let's move on to the next part. We've got our feasible region that is bounded. So we know we will have both a maximum and a minimum. We are interested in our minimum, so we're going to minimize our function. We have 3 corner points we need to check, and we are going to check them all. The coordinates of A, 0, 10, B, 4, 2, and C, 10 thirds, 5 thirds. So here, Z would be equal to 0 plus 3 times 10 is 30. For B, Z is equal to 4 plus 3 times 2, which is 10. And then for C, I've got 10 thirds plus 3 times 5 thirds. Well, 3 over 3 is going to simplify. You know what, let's keep our denominator the same though, because that's going to make me able to add them together. So I've got 10 thirds plus 15 thirds, which is 25 thirds. 25 thirds, if I plug that into my calculator to approximate it, if I want an exact answer, I need to give 25 thirds. But if I do an approximate answer, 25 divided by 3 is 8.3 repeated. So 8.3 repeated. And I'm interested in a minimum. So out of 30, 10, and 8.3, there's my minimum. And it's at that corner, 10 thirds, 5 thirds. Now, notice that I gave my coordinates exactly. Absolutely, I gave my coordinates exactly here. Unless you're told to approximate, you need to make sure that you give exact values.